and welcome to Statistics Video 2. And again, this word of warning, this may actually be video 8 in some areas because I'm doing this for 2 different streams. But this is part 2 of my regression and line of best fit analysis. So in this video, we're going to consider lines of best fit drawn by hand and using technology, although my by hand ones might be a bit different because I'll be using technology. We'll also talk about how to use different types of technology to calculate regression and apply them. So I'm going to talk specifically about Desmos and Excel, but you'll also maybe have a graphics calculator you can use, and you would benefit by considering how to do that, talking to your teacher about that. We'll also talk about how to use regressions to validate your solution. So here's the data from the last video. It's time against height for something. I'm suggesting it's probably a plant of some sort. And here's the graph of my data. Now, as we did in the last video, I can make predictions from that graph. But it's pretty hard. Like I made a prediction in the last video for 10 weeks. That's fine. What if I want to make a prediction for 100 weeks? And not only that, I mean, that's got a lot of risks associated to it because 100 weeks is a massive extrapolation. But I don't want to draw a massive graph. And if I did, my data is going to be cramped into one little corner and make it very hard to draw an accurate line of best fit. And I don't have a piece of graph paper big enough. So what we're going to do is look for a general trend. Now you'll see here that it starts at 0, 0, so it's not actually that hard. Just need to find how much is increasing by each week and apply that idea. But if we want to make a model here to make a prediction for 100 weeks, we're going to go to that linear model idea. So we're going to head towards a y equals mx plus c. And by variate data, we're assuming a linear trend, but you might have a reason to assume a quadratic trend, say it's a projectile, or maybe a periodic trend, say it's wave motion, in which case you'll have a different regression and different modeling process for that regression. But let's have a look at a linear regression and the linear trend. So the first thing, if you want to do this, is you want to find 2 data points in your set. They don't have to be part of your set of data. But look, I already know that 0, 0 is on my line of best fit, because that's the context, so I'm going to assume that. But I'm also going to pick another data point, which is up here. I can see it passes through that. And you're better off picking a data point up here somewhere rather than a data point that's quite close. Because picking a data point that's quite close might look appropriate, but it might actually lead you to inaccuracy because it might not be appropriate for later on. So you want that spread apart data points. So I'm going to use those 2 data points to make my linear model. So those 2 data points are 0, 0, and here that's 9, 30. There's my 2 data points. And going through the process, I'll notice that m is always equal to y2 minus y1 over x2 minus x1. So there's an average rate of change. And that's 30 minus 0 over 9 minus 0, which is equal to 30 over 9, or 3 1/3. But I'll probably stick with 30 over 9. Top-heavy fractions make life a bit easier in this case. Now, I've gone through this process. Finding the gradient was fairly obvious here, but you won't always have a data set that starts at 0, 0. So you'd have to go through this process. The second thing we'd have to do, again, it starts at 0, 0, but let's assume it doesn't, is we substitute in our new m value, which is 30 over 9x plus c, and then substitute in a point, let's say 9, 30, into our function to calculate the value of c. So if y equals 30 over 9x plus c, then I put 9, 30 in, 30 over 9 times 9 plus c. I get 30 is equal to 30 plus c, and c is equal to 0. Now, before you say, hold on a second, you've just done something blatantly obvious in a really difficult way, stick with me for a second. Again, I'm showing you this so that you can apply this method to a linear function that doesn't go through 0, 0. Obviously, we're given that the y-intercept is 0. You might get the y-intercept from here. It might be obvious. It might be there, say, at 25. Who knows? But you might not actually have data that's close to the y-axis. And if you don't, then you have to go to this line and put your gradient in and then substitute in one of the coordinates to find your c value. And that will work every time. So get used to that process because it will work for the harder questions. There's my function, y equals 30 over 9x plus 1. I can use that to make predictions. So I can say, therefore, at x equals 100 weeks, the y, which is the height, is equal to 30 over 9 times 100, which is approximately equal to 333 centimeters, 333 and a third centimeters to be exact. And that is a fairly good prediction, except for the fact that it's a massive extrapolation and we don't really know what happens between 8 and 100. I would assume that the plant will actually stop growing. Okay, so there is doing a line of best fit linear regression by hand, and that's developing the function by hand. Let's go down and talk about how we do it on Excel and how we do it on Desmos, and talk about the differences here. So if we go to my Excel file that I pre-prepared, here's my data. Now if I highlight that data, and just the data, it doesn't matter whether it's a column or whether it's a set of rows, I can go to this cell here and insert a scatter XY. I choose my scatter, choose this particular scatter, and there it is. Now obviously you can go through, you can change the title, etc, but I'll let you play with that. What's important to me is producing a linear function, a linear regression. So if you want to do a linear regression, the easiest way I think, you can do things up here for sure. The easiest way I think is just right click on one of the data points, and you'll see here it says add trend line or format data series or this stuff. I'm going to add a trend line. These options come up here. I can do linear or log trend line or polynomial, but I'm not worried about that. I just want linear. My linear trend line, when I say add it, I just say display the equation on chart, display the R squared value on chart, and if I move that to the side, you can see my linear trend line, which is y equals 3.4833x minus 0.933. Now, that's all good and well, but actually I've decided that my trend line should go through 0, 0, and you can see here it doesn't. It goes below 0. So if I actually say set intercept and then display, you see I get a new function. In this case, I don't have a C value, well the C value is 0. So now it's saying that my trend line is 3.3186, which is actually very close to the trend line that I got. What Excel will do is produce the best possible trend line. It minimizes the distance or the average distance of each point to the line. That's the job of Excel. Now by taking away my C value and making it start at 0, 0, I've actually increased the average distance, which lowers my regression. And so you'll see here I've got my function y equals 3.3186x. Below that I have an R squared value. And I'll talk about R squared values in a minute. But this R squared value is 0.9887. That's for the one that goes to the origin. My second R squared value is 0.9918. And my second R squared value is better because it's better to be closer to 1. So you're looking for a linear function and you're also looking for a better R squared value. You'll notice though that if I make a prediction here for 100, I'll actually get 331.86 centimeters, which is about 1.5 below the prediction I got from my function. So it's actually not too bad. So there we have it, using Excel and R squared. Now if I go back to my OneNote page and click on my other link, which is my Desmos graph, you'll see here that I've pre-prepared a Desmos set of data. And here's my data in Desmos. You can also make predictions in Desmos by using the tilde key. So I've got my data, it's labeled X2 and Y2. The tilde key is typically below the escape key, but you have to use the shift button. So it's above a dash next to the 1. But in some keyboards it might be in different places. So there's my tilde key, it's like a curly line. And then I say I want this to be, I want Y2 to approximately equal mx2 plus c. So if we have a look, here is my regression. Now it doesn't actually sketch out what the regression means, but it tells me the actual function, sorry. But it does tell me that m is 3.48333 and c is 0.933. If I go back to Excel, 3.4833 and 0.9333, they're exactly the same, because they follow the same mathematical process. So the computer's not making decisions, it's just following a set up, designated regression analysis process. And so we get this. If, on the other hand, I want to do a regression analysis, y2, and I've just typed y2, tilde, so approximately equal to mx2, this will do the regression analysis, but this time without a c value, or c equals 0. You can see my graphs there, which is this one's green and goes to the origin. And m is 3.3186, which is what I got in Excel, and my r squared is the same as Excel. And so we get that really interesting approach there as well, or result. So there we have it. Sketching on Desmos and doing a regression analysis on Desmos. You can do a regression analysis for lots of different functions. So for example, I could do y2 is equal to ax2 squared plus bx2 plus c, and I don't want an equal sign, I want a tilde sign, so, and it'll actually do, that black line there is a quadratic regression analysis. And the R-squared is actually better. So quadratic models this data better, technically, than linear function. But later on you'll talk about polynomials and why higher order polynomials are always better. In this place the context might be linear and provide that. And that regression of 0.9918 is very good anyway. So that's using Desmos. Go back, play with that, even try using my data and getting the same results. I just want to summarize one last thing before we leave, and that is the R-squared value. So the R-squared value is a summary or an average of the gap between each coordinate and the line of best fit. And it's done on a vertical basis, so how far away it is vertically above or below. That's it, and that does that summary. It looks at those averages and then provides a result between 0 and 1 of those averages, representing those averages. So basically, if R squared should be between 0 and 1, if R squared equals 1, then it's perfectly linear, which would be ideal, but unlikely. R squared is greater than 0.9, then it's strong, very strong correlation. R squared is greater than about 0.7, then it's reasonable correlation. And anything below 0.7, I don't think is very strong correlation. But again, you could go and read some textbooks, look up online. People will claim that 0.4 is good correlation. That's up to you, and it really depends on the context. You might have a context where you're actually expecting the data to be full of anomalies, or you might know there's an anomaly in there, which is going to wreck your correlation a bit. And you can deal with that by taking the anomaly out or just accepting that it's there and expecting a slightly lower R squared. So it is a variable thing, but in most cases I'd be looking for a correlation of 0.8 to 0.9 as a minimum to be suggesting any sort of strong or ability to use that function with confidence. So there you have it. Scatter plots using regression analysis and how to do it with Excel and Desmos. I hope you've had fun. All the best.